Thank you very much for attending this WorldDAB and ASBU DAB Plus technical webinar series. This is day 2. We've got quite a technical agenda today. But before we get to that, let's just look at some housekeeping. Now, we have a Q&A capability, and we certainly invite questions from all the audience, very much so. However, I do request that when you do want to ask a question, you use the Q&A facility rather than the chat facility. That will allow us to much more easily manage the questions and to answer those questions that we don't have time in the short Q&A time we have today. We have a longer Q&A session tomorrow at the end of tomorrow's session, so hopefully we'll be able to answer some additional questions then as well. Thank you for that. Now, let's see what we have today. So today we've got, day 2 is head-end systems and transmission systems. And speakers today are Arnie Borsum from IZT. We have Herman Zensen from Digideer. We have myself from ESCOM Technologies and the WorldDAB Technical Committee. And we have Rich Redmond from Gates Air International. So without further ado, I'd like to introduce Arnie Borsum, who's going to talk about encoding and multiplexing systems. So with that, please, Arnie, can you share your screen and commence your presentation? Thank you very much.
Okay, here we are. So thank you, Les, for the opportunity to present. So in my presentation, I'll rather focus on the component side of DAB headends and some general implementation options. And after that, Herman will give an insight into some practical implementations and experiences in the field. So before I start, I'd like to shortly introduce our company, IZT. We are located in Germany, in the city of Erlangen, and have been founded in 1997 as a spin-off of the Fraunhofer Institute here in Erlangen. Our portfolio includes a number of RF equipment, so for signal monitoring, signal generation, channel simulation, and other topics. In the context of DAB, chipset manufacturers, receiver manufacturers, and car makers use our signal generators and recorders to test their radio receivers. So, but today we are talking about DAB headends, and this is something where we are a long-term partner of Fraunhofer IAS for the content server solution. So firstly, what is a DAB headend? A DAB headend is a central component to process a number of audio and data inputs into a DAB multiplex, including all necessary signaling to be transmitted with the DAB signal. So that is, a DAB headend is the gateway between the content providers at the one side and the DAB transmission network on the other side. In some cases, the headends are operated by the DAB network operators themselves. In other cases, it is a broadcaster. So this depends on many factors, including legislation and other things. So functionally, a DAB headend encodes DAB plus audio streams from the audio sources from the studios. It processes and encodes the program associated data or non-PAD data services and generates the resulting DAB multiplex, including all according signaling, service information, and so on, which is included in the multiplex signal. The modulation is usually not considered as a part of the headend, but of the transmission network. So what we are talking about are the functional components which you can see in the yellow box in this slide. So several years ago, so legacy DAB headends consisted of dedicated hardware devices for the different functionalities. So apart from the multiplexer, we can see hardware encoders for DAB or DAB+, and in addition, we can see in this slide a PID server here for handling program-associated data such as dynamic labels to be inserted by the encoders. Nowadays, modern DAB headends build on integrated software systems. So in our case, the DAB content server contains all functional components of a DAB headend. That is a DAB, DAB+ encoding, data service handling, multiplexing, which are all performed by the same software system, including a configuration, interface, monitoring capabilities, and everything. If you look a bit more deeper into it, with according interfaces, you can firstly configure and monitor the system. From the signal point of view, there are a number of interfaces available for audio and data sources. And as this is a software-based system, the inputs and outputs are IP-based. So on the output side, there is EDI, which is the transmission of ETI via IP, is supported, which is supported by many transmitters nowadays. If not, you need an external EDI to ETI converter to feed the distribution network. With regard to audio sources, there are in general two possibilities. Either you can use the internal software DAB+ or DAB encoders of the software system, or you can receive pre-encoded DAB+ streams from remote encoders, which can be located in the radio studios. When using the internal audio encoders, audio can be provided from various sources, including audio over IP. You might know Livewire or Ravenna or other AES-67 solutions. If you have analog or digital linear audio available on site, you can use external converters to convert to audio over IP. In addition to that, RTP coded RTP streaming sources are available if you have contribution codecs in the field, or in the studio. They can be used to convey the audio sources to the DAB headend. Internet streaming is also a choice, but will usually lead to increased latencies. So this is mostly an option if you want to have a backup audio source, or for example, if you want to introduce a temporary pop-up station in a DAB multiplex. For data services, there are several protocols available. So it depends on the program provider which options are the best choice for him. So for example, dynamic labels and slides can very simply be provided as text or image file upload to an FTP. If you have existing FM RDS workflows, it is possible to attach to a UECP stream. And there are also modern application interfaces which can be used to provide data and signaling. So I will just quickly show some examples. So with the protocol JSON RPC, it is possible to provide labels or slides. So as it can be seen here, so there's a syntax where you can provide the PID in this case for a service. In addition, there is a web interface. So usually this is rather a choice if you have static or repetitive text, which shall be used as dynamic labels, but not for something which is dynamically fed by a player out system. So I'm coming to some implementational aspects. So as I said before, modern encoder multiplexer platforms are integrated software solutions, and this makes it quite easy to deploy them on standard IT server hardware. So they come with an integrated operating system based on Linux. You have a web interface, which will be shown briefly later. And if we provide turnkey solutions to operators, we will use highly reliable standard server hardware with hard drives in a RAID configuration, dual power supply, which makes them very reliable in the operation. And also it's possible to very easily replace spare parts or to migrate to a new hardware platform some years later. Another option, as such a system is software-based, it can also easily be deployed as a virtual machine. That means that a DAB head and could also, or can also be operated in a data center, either third party or your own data center. So there's one virtual machine per multiplexer, per content server instance, including all the multiplexers and the encoders. So virtualization allows very flexible network management and routing. So there are pros and cons. So I'm just briefly discussing those. So of course, using virtualization in contrast to dedicated installations on dedicated servers, you have of course some cost saving because you save own rack space. You have some standardization in your infrastructure, IT wise, and connectivity. But at the other side, the cost savings are mainly rack space, but you will have increased efforts on the operational side. So it is more complex to handle synchronization, timing. You have to consider the cost for transferring data from or to the data center. And also the overall reliability depends on additional factors like the hosting infrastructure, the connectivity, and also other applications which may share the same infrastructure. Just briefly mentioning the web interface. So the web interface allows to configure general system parameters, audio and data services, services, the multiplex. So all the configurations which can be done are fault proof. So it is not allowed to apply an incorrect configuration. And all configurations on services, subchannels, and the multiplex are done on the web interface, and all the DAB signalization, which is related to that, is automatically derived from those configurations. So there is no need to manually handle any service information, FIGs, and so on. So this is an example of the subchannel configuration where you can configure the encoding, the bit rate, the error correction, and so on of a subchannel. In addition, there are several interfaces available to, for example, activate a multiplex configuration, to signal, for example, announcement or alternative frequencies, and a monitoring system provides system status with fault notifications over email or SNMP. And if the operator wants to analyze that further, there are also detailed log files available for a detailed fault analysis. Okay, I'd like to discuss some redundancy approaches. So firstly, if you install the head end, you can simply put one system into operation without any redundancy. And as seen before, by using this highly reliable IT hardware, the probability that something fails is quite low already. However, if the hardware fails, you won't have any backup. So the first option would be to have a cold spare, as we call it. So you could have a reserve hardware platform available, which could be put into operation if the main system fails. The next approach is to have a full 1+1 redundancy. So two systems are combined to a redundancy group and will share all configurations, schedules, content, and so on to be identical. And they will also feed 1+1 EDI output streams to a redundant network feed. So, and there's also an enhanced redundancy also between the stages of the processing chain within the DAB content server system. So this means that the encoded audio streams are shared between both systems, as well as the EDI multiplexer outputs are shared, such that it is possible to feed some bit identical EDI streams to the network, to the transmission network. So this highly increases the reliability of the system. So I'm coming to my conclusion. Modern DAB multiplexer systems provide a flexible and scalable functionality of a complete DAB headend. And the implementation options allow a smooth integration into existing and new infrastructures. So if there are any questions, I'm happy to answer those in the Q&A session later. Thank you very much.
Thank you very much, Arnie, for that presentation. That's very clear, very interesting capabilities in the system you were presenting there, and also some good insights into the way that DAB multiplexing and head-end systems actually operate. I've had a couple of chat points about the presentations today, and I'd just like to tell everybody that the presentations today will be available on both the ASBU website and the WorldDAB website. So you can go there maybe half an hour after we finish, and you'll be able to download those presentations so you can then go and review them. And if there's more questions that come from that, that's fantastic. So now, however, I would like to present Herman Zensen from Digideer, Sales Manager at Digideer. So please, Herman, over to you for your presentation. Thank you.
Okay, good morning, everybody. Just give me a second to share. Okay, sorry, I'm ready. Yeah, good morning, everybody from France. My name is Hermann Zensen. I'm the sales manager of DigiDia. First of all, I would like to say a big thank you to WorldDAB and ASBU for having us invited for this presentation. It's a big honor for us, and particularly thanks to ASBU, because I know it's not so easy to host an event like this. In my presentation, I will give you a short overview of our company. Then we will discuss the two main architectures that we have for DAB headends, which is centralized architecture and distributed architecture. And I give you some examples of realizations that we did in the world. And I will have a short conclusion after this. Yes, well, DigiDia, we are based in France, in Western France, more particularly in Brittany. So the capital of Brittany is Rennes, so we are in the north of Rennes, and you can see on the slide, you can see some photos of Brittany. You see we have forests, we have sea, it's a beautiful place. I have been living here for more than 20 years now. I'm born in Germany, but it's worth a trip, but this is not why we are here. We are here as a high-tech company because it's one of the main high-tech regions in France, and you have many broadcast companies such as also NNCs, Teamcast, Thomson, they come from here, okay. It's easy to get good engineers here. And to give you the complete picture of our company, we are not alone. We have a sister company. We bought them 10 years ago. It's called Kenta. Just to know for you, yes, this company, they will, yes, they're specialized in maritime communication, air traffic communication, inland waterway communication systems. So so if you're looking for systems like this, we have it here in Brittany, okay. DigiDia, obviously, we are specialized in digital radio. Both companies together, we have around 2.5 million turnover and 14 employees. We are international, we sell all over the world. And we are not a startup. We have been created more than 15 years ago by 4 former Harris Gates Air employees. Okay, we are a spin-off somehow of Gates Air. And our engineers were the very, very first one that over 20 years ago started to develop the first DAB encoders and multiplexers for a company called ETIS that was bought later than by Harris. So we have a lot of experience with DAB. We are R&D oriented company. We do hardware and software. Everything is developed internally. We have more and more, we are doing software defined radio designs, especially for modulation and demodulation, okay. This is also what we use for the products for the maritime communications, for example. All our products are IP based. And on the right side, you can see our 3, you see 4, but mainly we have 3 product lines, which are DAB, which we are here for. Then we also do DRM, which is to make it easy for digitizing AM. And we also have a technology, synchronous FM, which enables you to have single frequency networks in FM, okay. So for this, you have to do some tricks to avoid the interferences, and the tricks you have to use are very similar to what you have to do in DAB single frequency networks. Here for the products, you can see we have products, 2 types of products, but some are based on PCs, others are based on FPGA platforms. So if you look at the things like this on the right side, all our headends are software based, completely software based. So this is true for DAB, DRM, and also for synchronous FM. So you can have it on our own platform or on a virtual platform, whatever you want. We have also FPGA platforms, which we would use, for example, for the EDI, ETI converters in DAB, or for exciters or modulators for FM and for DRM plus, and for DRM. And then we also have mixed products, such as the product you can see here below. This is our tunnel breaking product. For this product, yes, you will need to have a DAB, small DAB receiver, small DAB transmitter. And for this we use a PC platform with PCI boards that hardware developed by ourselves. Okay. Yes, this is just to show you, yes, we sell all over the world, mainly in Asia and in Europe, okay. Yes, in Europe, a little bit everywhere, but in Asia, we have good sales in Japan and India, Taiwan. Okay, we have done some sales also in the one country we have done in the Arabian countries. It's Algeria. Okay, and yes, but for the rest, it's for us still a region where we hope to sell in the future much more. Well, let's come to the DAB architectures. When I started to prepare my presentation, well, I took it from the FM side. You know, if you know already DVB, then I think the DAB is quite easy for you, and also the headends are very easy for you. But if you come from FM, yeah, typically people will say, okay, they used to have one transmitter with an audio input, and you can be immediately on air. If you want to do this in DAB, it's a little bit more complicated. Yeah, you need not only a transmitter, you also need a multiplexer. And as Arne explained already, what is the multiplexer good for? The multiplexer will not take only one audio, it will take several audios. This is the difference to FM. So you have more than one audio in one stream, okay? And you will multiplex them, which means you bring all this together and you have one output, which is now in the modern architecture always IP EDI output. So this means a DAB transmitter typically has an EDI input and then a digital modulator with an amplifier behind it, okay? So this is, if you want to say, for example, want to start with a trial, this is the minimum system, the minimum you would need to start with DAB. Typically, I'm just showing this slide. Okay, of course you can then add, it's not necessary to have one multiplexer for each transmitter. It's enough to have one multiplexer to cover all the transmitters. This is a big advantage of DAB and also of DVB, of all digital modulations, okay? So it's enough to have one. Once you have the multiplexer, you can easily add transmitters. You can use them single frequency networks and add coverage like this, okay? This is a slide to have a look inside the system. You saw this already with Arne. Okay, so we have in a DAB headend, typically we have always a multiplexer and we have DAB encoders. Okay, so we always have encoders, multiplexers together. And for the easiest system, you need to bring somehow the audio to the system. Easiest way to do it is with sound card and live audio. Okay. Yes, you get EDI out. Yes, if you look at the presentations that will follow here, the gray one, this is a hardware platform. It can be a hardware platform or virtual machine. Yeah, and on this one, typically you will have all the SNMP part and the NTP part. And the white part, you can see this is the head and the multiplexer software. Okay, so if we go for a simple centralized system, okay, you can see that you can have, at least with our system, you can have, for example, you can have on one virtual machine several multiplexing systems that will bring out several EDI, okay? And you can add, if you want, you can add more platforms to have a bigger headend, okay? The modern systems, you know, I told you already for the transmitters, it's IP-based, yes, the distribution network, but also the contribution is IP-based, okay? So it's enough to have a good IP link, your own VPN, for example, to bring the content from the studio, the audio from the studio to the multiplexer. Now, you can see here, we call this is a centralized architecture because the studio codecs that you use are standard audio codecs, okay? This is, so this means you can use standard products, I don't know, from Digigram, from WorldCast, from any company, you know, Gates Air, whatever you have, 2WCOM. There are many companies that do this. They're specialized for audio contribution. You can use this, it's very similar to audio contribution also for FM, okay? So it's enough to have a good audio contribution. You bring this to our headend, and in the headend then, this is also what Arne explained, you will decode the incoming audio, and then encode it again in what we say in DAB+, in the AAC of DAB+, okay? So there are many standards that you can use for the contribution, okay? If you want to go a little bit further, what we see typically from customers is they say, okay, now we would like to have input redundancy, okay? This is typically the next step. For input redundancy, we have a feature we call a smart audio multiplier. So you have audio in this multiplier. What do we do? We have one flow here, which is a high quality IP audio codec. For example, it could be MP3 over RTP on a high bit rate. Okay, that you use, yes, that you decode and you transform it into PCM over RTP. Then you can have another flow for redundancy, which is IceCast. This you can take on the web with a much less, can take it on the open web. Typically you get this on the website of the radio stations. And as a third security, you have an audio file, a pre-registered audio file. So in the audio decoders, they will all give you a PCM output, and then we have, they have some intelligence in the switch that will automatically take the best audio. So if you add this component in the system, you will have a system a little bit like this, which is same as before here. This part is the same as before. You have a DAB headend. And on a different virtual machine or hardware platform, you will have then the smart audio multipliers. The smart audio multiplier, okay, it will handle redundancy as explained, and then it multiplies. It means it will send, the PCM over RTP stream to all the encoders, all in the different multiplexers, and typically install it on a different machine. The next step, what we see here is the same architecture we saw before. We have now some monitoring in it. To give you typical, the monitoring software we have is exactly the other way around of the FlexiDAB of the multiplexing software. This means you will have a demultiplexer and a decoder, and after the decoder, you will have then the audio monitoring. I can send you one typical screen that is used, for example, by TDF. So here you have a screen, typically the big broadcast operator, they have one big screen that they can see immediately if all the audios are okay. You have a screen like this that you can use for monitoring. So here you have 3 multiplexers and you can see some radios are okay, others are not. You see it immediately. And yes, and the last, looks quite complex architecture, but it's the same as before, but you just have now a redundant centralized architecture. So this means you have 2 redundant multiplexers that, that supervise each other, and that have the feature, this you can see it here, this is the EDI feature that was described by Arne before, okay? And that makes sure that you get out always the same identical EDI stream to everything. Now, to compare the centralized architecture, we have, in contrast to the centralized architecture, we have a distributed architecture. You may say, okay, this looks quite similar to the slides you saw before. The difference is here on the left side, you have a specific DAB encoders, okay? And you get out the DAB encoders, okay, you do the encoding in the studios typically. You get out what we call an SDI stream, okay? So it's a specific stream that is standardized in DAB. You bring it over an IP network, the same thing. You can bring it and then to the multiplexer, and the multiplexer just takes it as an input and will only do the multiplexing. Okay. You have some green slashes here. We have flashes, green arrows, sorry, that you can see for the encoding of the data. You can do it in the studios, or you can do it in the multiplexer, similar to the things that Arne explained before. And there's some advantages and disadvantages. What's important to know with this is that you need to have a communication between the DAB encoders and the multiplexer. Okay, so you have to define some exchange protocol, which is in our case HTTP based, but it's specific for each manufacturer. So this part is not standardized. Now you can do also redundancy, input redundancy, but then we don't do it with smart audio multipliers. It's enough if you have 2 redundant audio encoders that will send 2 different SDI streams, and then you select with a in the multiplexer the SDI stream that's working best. But you have you need to have in this case 2 identical redundant encoders to realize input redundancy. And the monitoring is exactly the same as in the centralized system. So this slide doesn't show any. So you can use it's the same EDI that comes out for monitoring is actually the same thing. And yes, the redundant distributed architecture you can see here. Yeah, you add the EDI stream, and yes, you can have it on several. It's exactly a copy. So you have 2 identical. They need really to be identical, the 2 on the software option side, that you have the same encoders and same multiplexers to make this hot redundancy. Okay, just some thoughts about what, we prefer, highly prefer the central architecture. There's one advantage with the distributed architecture. That's you know, the people that like it, they always say, okay, you don't have transcoding in these architectures. You can do the direct DAB encoding, bring it over the IP to the multiplexer, and so there's no decoding and re-encoding. Okay, this can be an advantage, but the disadvantage with the system is you need to have a communication, what I told you already, between the encoders and the multiplexers. It's not standardized, and it can be very, very complex, especially if you allow the studios to say, okay, you can change your bit rates and things like this. You can change your settings then you need to have a discussion between the encoder and the multiplexer to decide if this is really allowed or not, okay? For example, a studio could say, I want to have much more bit rate, but if the multiplexer doesn't have it, then it's not possible. So we think if you want to realize, if you want to give hand for radio stations on the multiplexer, we have a feature which is called virtual service multiplexer. It's much better to give them, you know, a part of the ensemble multiplexer, a centralized system, and that they can do on this part whatever they want. And we can, whatever they want within the rights that have been defined. And this is much easier because you don't need to communicate, you can decide immediately if it's okay or not. And obviously, we also think that the audio contribution is a different expertise than DAB. It's now we have on the market good standard audio codecs that can give you a very good audio contribution. So one of our, I give you some examples of the realizations that we did. This one is for Slovakia. It's the very first thing they did there. So here you can see, yes, this would be a good setup also, you know, in any region for a first system. So you have 18, here you have 18 DAB encoders on one multiplexer, okay? And they added some data features like electronic program guide, TPEG, BWS, journal line. But what you can see, this is exactly what I explained before. It's a centralized system, so you have an audio over IP decoder before, and then you for each audio you decode and then you re-encode in DAB. So this is the easy system. You can see here they use a special format, UACP. This is a special development we did for them. You know, this just to let you know we can do some special things. UACP, you may know, comes from radio data system. So it's more from FM, but you can get information from FM, for example, for text and things like this that you bring in DAB then. It's not standardized for DAB. And then they started with redundancy. Well, how did they do the redundancy? The first system they had, they installed it simply on their own server, okay? And the second system they had, they installed it on their own virtual machine, okay? Which they ran on one of their servers, okay? So we just doubled it and we added the EDI switch. I show you this architecture, which is, looks quite complex. We installed this 12 years ago in Hungary. It was really, yes, at that time, a very, very modern system. Yes, and you can also see some things that you don't need anymore. But yes, you see it's a distributed architecture, or mix. It's a mix between a distributed and a centralized architecture. So the public broadcaster, he had 8 DAB encoders with PAD on their side, and then the other private radio stations, they had a centralized encoder system at the ensemble multiplexer with 10 encoders, okay? You can see the blue ones, these are our audio panels. This is to bring in the live audio to the system. We can still do this, but today, for the modern architectures, it will be more over IP, or AES-67, for example, if you don't want to have compressions. You can see things that you don't need anymore. For example, here the GPS receivers. Today it will be over NTP, okay? You can see ETI. I think if you buy a new transmitter, you will only have EDI, okay? So you don't need the converters anymore. And yes, you can see it's both are redundant, okay? The encoders and the multiplexer. Well, at that time you could, you know, today we have more and more virtual systems, but at that time you can still take some photos. You can see, okay, you have the audio panels. These are the audio panels above, and then you have the our DAB head-end on a 4-rack unit PC platform. This is the GPS receiver, and you have the ETI switch, EDI switches below. So you can have all this in one rack, which was at that time, yeah, typically it was revolution. This is an architecture to finish. It's an architecture that TDF uses in France. So they separated the encoding part from the multiplexing part, mainly, yes, for cost reasons. So you can see you have 50 encoders on one PC platform. Okay, on the other PC platform, you have something like 8 multiplexers. To bring this encode from the content from the encoders to the multiplexers, you have SDI. EDR-OFS. So you need something like 4 SDI flows to bring the 50 to the multiplexers. And then, yes, we have in total 8 multiplexers. And yes, today we have 2 systems like this. This is only half of the system we have with them. We have a double system like this. You can see for the contribution, they use MP3 over MPEG-TS for the high quality audio, and they use IceCast for the lower quality audios, okay? They get it from the web. And we have also a feature that we can get metadata like text or slides from the IceCast flow and integrate it directly as a slideshow and text in DAB. Okay, to come to the conclusion, okay, the modern DAB headends are completely software and IP based. You saw this from Arne, you saw this from us, and therefore it's compact systems, easy to install and easy to maintain. We can do this even remotely. Modern contribution and distributions are IP based, so it means you need expertise for IP networks, but I think for most of our customers, it's now much easier to take care of an IP network than of old E1 or G704 networks. We can have virtualization or set up on dedicated servers at customers. This is possible even for complex architectures. It's possible to start very quickly a cost-efficient trial with 1 transmitter on 1 DAB headend. You can have a very compact, small system for a trial. And yes, basically to sum it up, the DAB rollout is today much easier than 10 years ago. Okay, this was it for my part. Thank you very much for listening.
Thank you very much, Herman, for that very interesting presentation. I think we've got some time now just to have just a couple of questions on Q&A. I've got the first one here from Adela, and it's to IZT, to Arne. And the question is, SRT streaming, is it supported on the ICT MUX DAB server?
So the short answer is no. So for RTP streaming, we support the AAC and MPEG family of contribution codec formats. So as far as I know, SRT is an open source codec. So if you want to use that as a source for the DAB encoding, this is not directly supported by the software system. So you would have to install a separate SRT decoder to convert to a PCM format for later transcoding. So it's not directly supported.
Okay, thank you very much. I have one more question for Arne from Assam Badredineda. Sorry about the pronunciation. For question for IZT, can you tell us more about the URL call for MUX activation?
Yes, so of course it's a bit more complex than I can tell in a minute now, but if I'm allowed to share my screen for some seconds.
Please do.
Give me a second. So it would look something like this here. So can you see that? Sorry, to rearrange my windows on my own screen. So to activate a multiplex with this URL call, so the syntax would be something like that. So you call a so the multiplex configuration will have an ID like multiplex daytime, for example, and the URL call would accordingly look like something like this below here. So it's practically a URL call with those parameters over here. And in addition to that, there are also timing parameters, so that you basically can say at this point in time, a multiplex shall be activated. So if you need more details about that, don't hesitate to contact us. But that's what I can tell in, in the short time I have.
I think the important thing there is it's all possible. It's just a matter of getting the details to move it forward. One quick question for Herman, and we'll move on to transmission. There's another question from Assam for Digideer. What is the advantage and the inconvenience for having one MUX encoder equipment and having a separate encoder and MUX technically? Is it bitrate, cost, must use one? Does that make sense to you?
Yeah, I think this question is related to this last slide that I showed about TDF, because they separated the encoding from the multiplexer. How to say? It's the advantage of this. It's mainly a cost advantage, because they just need to buy one encoder. They encode it, and then they can distribute with multicast this encoding to all the multiplexers. This is how I understood the questions. So, but obviously, well, to be honest, we prefer to have a multiplexer with more than to have it in one box and not separated. But it was a customer's choice, and then you know, for the cost of the how to say it, of the encoders, this can always be discussed on the sales level. Then, you know, but it's from a technical point of view, it's easier to handle everything in one multiplexer. Was this the answer to the question?
Okay, that's great. Thanks, Herman. I think we need to move on now, and we'll move on to transmission. I'm going to now give a quick overview of transmission systems, and then we have a presentation from Rich Redmond from Gates Air talking about the details of transmitters. And after that, we'll finish off with a further Q&A session. So let me kick off here. So I'm going to look at two things. I'm going to look at transmission system overview and monitoring systems. And the main system blocks, which you've seen some of in the other presentations this morning. We start with our Ensemble multiplexer, and of course, before that, we'll have encoders and distribution, contribution really, for those multiplexers. And those multiplexers feed a transmitter in some way through some sort of network. Usually today, that's through an EDI network, an IP network. It could be a telco, it could be a private microwave link. And we can have multiple transmitters at a site, and the signals, the RF high-powered output signals, are then combined together. They're usually then fed to an antenna switch frame if the signal is, and the antenna system is big enough. And if we're that lucky, we've got a big antenna, we can have an upper and lower section for redundancy. So here's an example diagram of the ABC SPS network, just showing the complexity here. We have, on the right-hand side, we have 5 transmitter sites. On the top, we have 3 studios, the bottom, another 2 studios. We have 5 studio sites. And then we also have 2 head-end sites, which are also studio sites and act as a redundant pair. So both sites actually multiplex all 5 ensembles together at each site. So it's a disaster recovery scenario as well, to some degree, and then output all of the ETI over IP to the transmitter sites. So this is an example, probably more simplistic than what Herman was talking about for TEF, which has got an even larger footprint than the ABC SPS in Australia. Modulation encoding, I just want to point out where this happens. We talked about audio encoders. Well, that's where the audio encoding happens, of course. In the multiplexer itself, while the multiplexer combines all the signals, all it really does is apply the Reed-Solomon encoding for DAB+ for the individual service streams and provide some time interleaving as well. And all of the rest of the signal processing, the channel coding, the time interleaving, the multiplexing of the systems, of the signals themselves into one stream, is actually done in the transmitter. And then that goes to frequency interleaving, the OFD, the modulator, and that goes to the PA. So just so it's clear to everybody that a lot of the actual RF signal processing, you might call it, the signal processing to get the signal on air is actually done in the transmitter. It's the multiplexer that actually brings all the signals together from the studios into one stream, and the digital signal processing of that, the transmission is done in the transmitter. Now, that brings me to the actual error correction itself. And in DAB+, we have two sets of codes, actually. We have the rate A codes and the rate B codes. The advantage of the rate A codes is they have an 8 kilobit per second amount that you can increment in. So 8, 16, 24, 32, 40, whereas the B codes actually are in segments of 32 kilobits. So we mainly use A codes, and what we use for fault error correction is a code rate 1/2. It's code rate 3A. That is by far the most commonly used code rate, and that's because it's got a very good balance between protection of the signal, the error correction, and the power required. Now we can, and the capacity, sorry. So rate 3A, we have a capacity per multiplex of 1152 kilobits per second. Now we can add additional coding. In fact, we can go to rate 1A, which is 1/4 rate coding, so it's twice as strong as the normal 3A, but what happens is our capacity is halved. So we get only half the capacity. So instead of 18 services at 64 kilobits, we have 9. But the advantage is that the amount of power to cover the same coverage area is between 3 and 6 dB less. So it's 2 to 4 times less power you need. And that has quite a significant impact on the cost of transmitters and antenna systems. So for example, to go, if you use 1A, you might have an array, an element array in antennas, which has only got half as many elements in it. So it's going to be maybe half the price, or the transmitter's half the power, or even a third of the power. And I say it's -3 to -6 because it depends on the conditions. If you have very heavy shadowing, you might only get a 3 dB gain. If you have relative line of sight or Ricine channels, it's more like 6 dB. And we can go the other way too. We can have weaker error correction to get additional services. In this case, it would be 27 in rate 4A, 27 64 kilobit services. But to get that, you need 4 times the power. So we have trade-offs, and different situations can use those. If you don't have too many services, you can have higher code rates. If you've got a lot of services trying to get into the same mux, and we've got some of those in Australia where in one case we have 27 services on one mux, some of those services are on weaker error correction. Let's move on. Okay, let's look at the antenna systems. Antenna systems are critical. You might notice I'm jumping right over transmitters because Rich Redmond will talk all about the details there. So we've jumped from the encoding aspects in a multiplex, in a transmitter, straight over into combiners and antennas. And here's a few pictures of typical combiner systems. The one in the bottom right-hand corner is a photo of the DAB transmission in Sydney. And you can see there a triple combiner system. So we've got 3 ensembles in Sydney. Now, combiners or filters are required to have suitable attenuation of out-of-band signals. And we see here on the right the spectrum mask that comes straight out of the standard, and it's quite quite a significant amount of attenuation, let's say. Why is it like that? It's structured like that to allow multiplexers to sit right next to each other. Now, our signal bandwidth in DAB is 1.536 megahertz. Our channel bandwidth is 1.712 megahertz, which doesn't leave much protection between ensembles. And the reason we can do that and make the transmission very spectrally efficient is because of the use of these critical mask filters. And in fact, we can see what happens here. A typical output spectrum from a transmitter will have a noise floor of somewhere around -40 dB relative to the main signal. However, what we actually need is 80. So in more detail here, this is typically what we will get from that mask filter. That's the black signal is the filtered signal. So the adjacent channel interference has been pushed right down to -80 dB. There is some at not quite -80, between -45 and 80. And because of the nature of the signal, that's enough attenuation to still allow the use of the next channel, which would sit right next door in this area here. So this is a really important aspect. In fact, in Sydney, Australia, we use multiplexers on frequency blocks 9A, 9B, and 9C right next to each other, and everything works very well. So very, very useful. And here's just some stats of and specifications for some of the mask filtering. Just remember, you don't get filtering for free. It does take some power, even with cavity filters. These are mechanical filters. You can see all the adjustments on the right-hand side here. It can be quite a complex operation to get a very good filter specification, or combiner specification in this case. And a typical loss through one of these systems is about 1 to 1.5 dB. Here's a source spinner. Their systems 1 to 1.3 dB and the center frequency. So when you're going through multiple of these combiners, you do need to take into account you'll need extra power for the one that's at the front, the beginning of the chain. The one at the end of the chain, closest to the antenna, will have the least attenuation. But in a set of 3, it means that the first transmitter is around 3 dB more than the last transmitter. Worth noting that. Some examples of towers. Pardon me. You see here one on the left, that's the tower in Sydney. It's just a standard tower with multiple antenna systems on it. The one on the right is an antenna system in Hobart, and that's a very, very onerous site, and it has a full radome. And what we had in Australia also, and you might have in your country, if you're using VHF for digital television, we wanted to use the same sites and the same towers, because those sites and towers are quite scarce. They're usually on very high sites, which are difficult to get access to. So what we had to do is actually do dual polarization antennas. These were all panel antennas. They're very high gain arrays. And we had to convert from what was previously the horizontal polarization for television, because we have 5 digital television channels on the same panels, and we have the 3 vertically polarized DAB signals on those dipoles. So we use the combined dual polarized antenna panels to make sure we could use the same aperture on the same towers. Very cost-effective solution at the end of the day, much cheaper than building a new tower on a new site. And of course, with antennas, we have to be careful to make sure we get the right signal power in the right direction. So here's our horizontal radiation pattern in Brisbane. And what we've got here is a very deep notch to the north. And that was originally there to protect analog TV when we were doing analog switchover of television, analog switch off of television. And we have some other points here to protect other license areas, not so deep, only about 3 to 4 dB. This notch in the north now is not needed anymore. So there's negotiations at the moment to actually redo this pattern to make sure that the power to the north, to allow good coverage of the license area, is possible. Now, not all sites need a lot of power. Some are quite intermediate, and typical, 6-bay dipole arrays are quite common. And for even smaller systems, we can go to Yagi antennas, for example. There might be a few hundred kilowatts as an infill. So there's a full range of different antenna types that can be used. I'm now going to switch over to monitoring and very quickly go through this because I'm aware of the time here. And monitoring is a very, very important thing to make sure that you keep control of your network. You understand that it's working correctly, and that if there is any issue, you can get to that very quickly. So our signals will go through multiple different equipments, through multiplexing systems, through transmitters, to the actual antenna itself, and of course to the listeners through the RF channel, and maybe through some additional infill transmitters, or you might have a single frequency network operating to get coverage of the area required. And often we'll have a network management system. So what does that listen to? It looks for ETI monitoring, so the output of the MUX. That could, these days, that's more like an EDI monitor. It looks at the output of the transmitter to check the power and the quality of the signal. You can have a field monitor look at the field strength out in the field. You can have single frequency network monitors to make sure that when you have a single frequency network, all of those transmissions are within the appropriate timing boundaries. You have a service monitor in studios to make sure that your signal off air is good and you're not getting problems with maybe some of your program associated data, for example. And in some countries, it's also legislated that you have to record the signal off air for a certain period of time. In Australia, that's 60 days, just in case someone says the wrong thing. And we have to go back and check. Or maybe an advert wasn't displayed correctly or broadcast correctly, and the customer wants to make sure that they're getting value for money. Nowadays, network management systems can be quite complex. They're usually SNMP based rather than old relay systems. We trust IP these days and get some pretty fancy setups. And what is also quite nice to have in monitoring is to have mimic diagrams. So you can see the signal flow through various parts of the system. In this case, it comes from a MUX, goes through some sort of DA. This is a system built 10 years ago, through a changeover switch, to an exciter, to a power amp, through a baseball switch, out to an antenna system. So we can see the full flow, and if any of those parts fail, we get notification and we can see there is a failure, and it switch to operational parts and then go and correct the fault. Very handy. So in summary, transmission systems need to be engineered to meet the business demands for both coverage and interference. We'll cover more of that tomorrow in network design. And reliability. And of course, performance and cost effectiveness are absolutely critical. These days, they've always been critical, probably more so now though. And monitoring systems are essential to ensure that you are getting the right reliability, fault protection, detection, recovery, and future-proofing for business. So a lot to think about there, a lot to do, and happy to answer any questions on that later on. But for now, I think we're going to move on to Rich Redmond. He's the president of Gates Air International, and he has a video to show, because he's in the United States and the time difference doesn't really let him do it live because it's 3 a.m. But we have a nice video from him to play to you now. So please enjoy this presentation from Rich Redmond.
Hello, everybody, and welcome to the WorldDAB webinar series. We'll be talking today about advances in DAB transmission systems. My name is Rich Redmond from Gates Air. Glad to participate, and thanks everyone for making time to discuss DAB transmission.
Sorry, issue here.
So for today, the agenda, we're going to talk a little bit about some of the transmitter options for DAB networks, from very low power transmitters to much higher power transmitters. We'll talk about advancements in energy efficiency that have taken place over time and why that's relevant to us. We'll look at the considerations of where you might use a liquid or air-cooled transmitter in your network, because the applications are pretty different. We'll take a look at some of the redundancy operations that you can choose. So these could be both the redundancies that are built into a regular transmitter, and then some of the configurations you might be able to use to back up your system or multiple systems. And we'll also talk a little bit about link redundancy, type of redundant options you might have in an IP network, for example. And then, you know, a lot of times we think of transmitter sites being one transmitter for one channel. That's traditionally been the way an analog system works. DAB in its nature is a multi-audio channel or video channel, if it's DMB, per transmitter. And so we have some solutions that actually go beyond that, and we'll talk about how we might have a multi-transmitter system or multi-carriers on the same transmitter. So to start, if we just think a little bit about the structure of a DAB network, you know, kind of in a signal flow from left to right, you know, and others will be talking about these other portions of the signal flow, but there's multiple audio sources through encoding and multiplexing that gets distributed, at least on an IP network, over EDI protocol. And then we can accept that natively in the transmitter. So if we think of this signal flow, the area we're going to talk about is going to be on the right-hand side. So transmitters, typically we think of them somewhat by the power level and also by the cooling methodology. Here's an example in the Gates Air product portfolio. Other manufacturers would have some similar characteristics, but at very low powers, they're usually a very compact transmitter solution, maybe 50 to 150 watts. Mid-power transmitters we might see in the several hundred watts to kilowatt range. These are all typically air-cooled. In this portfolio, we go up to a fairly high power level, 13 kilowatts in digital power. In air, and then liquid cooling starts a little over a kilowatt and can go to very high power levels with multiple cabinets of about 45 kilowatts. So we'll talk a little bit more about those as we go through the portfolio. When I think about DAB transmitters, especially the ones that are probably most common in most networks, very compact, some unique advances, high efficiency Doherty PAs. Doherty's amplification methodology that allows amplifiers to be far more efficient than, you know, where we were even 4 or 5 years ago. Contemporary transmitters also have native EDI or IP-based inputs for the ensemble transport stream. The traditional ETI or physical layer is also available. In our case, we have some replaceable front panel modules that allow you to choose what type of input facilities that you have. Transmitters have adaptive pre-correction built in, or RTAC in our case, real-time adaptive correction, and we can achieve very high MER ratings, 33 dB. Now, it's important to note, especially if you're comparing to a lot of television nomenclature, MER, because the DAB waveform is very, very robust and much simpler than that of, say, DVB-T2, an MER of 25 or 27 is actually quite good, and increasing it above, you know, in the 30s while it does give you some improvement, it doesn't give you the same level of improvement you might have in television. So when doing your network planning, you know, the trade-off of transmitter efficiency and size versus MER is one that MER doesn't need to be generally protected as much as it might be in television. Now, in our systems, these transmitters can be configured in multiple ways as a transmitter, and so that's defined as taking a transport stream in, an on-channel gap filler, meaning I take frequency 1 in and then I rebroadcast it on the same frequency to be used in an SFN, so it's off-air pickup and then a rebroadcasting, or a transposer. I come in on frequency 1 and I transpose it to frequency 2. And the other thing we'll talk a little bit about is all of these need to have very modular and simple plug-in power supplies and PAs. This is an advance that you'll see in some of the products, specifically the ones we offer. Now, to give you an idea of power levels, again, in these very compact transmitters, so in 1 RU, you know, market-leading products will deliver 80 to 150 watts, depending on the amplifier selected. In 2 rack units, you know, upwards of 450 watts, and in 3 rack units, 750 watts. Now, this is a significant advancement. One is compared to where state-of-the-art products were 5 or 7 years ago. So if you've got a network that may have been deployed in the past 10 years, there have been significant advancements in the ability to make compact and high-efficient solutions. But even when you look between competitors, not everyone offers very compact solutions. Now, where this can really benefit you is when you're paying for the amount of space you consume at a transmitter site. Having compact transmitters allows you to save money on your network deployment costs. So if we zoom in a little bit closer on what you might see in a contemporary transmitter, as I mentioned before, it's all about modularity. So in this product, we can see there's multiple input slots where we can take ETI or EDI in. We also have off-air receivers for the transposer, and we have satellite receivers to directly feed the transmitter. Front panel touchscreen for control, Ethernet port to go to a TCP/IP-based web browser and SNMP protocol. And then when we look at the rear, all the typical connections you would expect with RF out, inputs for GPS with 1 PPS connections, cooling fans, which are removable and replaceable from the back without having to turn the transmitter off. And all of these are modular and simple to replace. Now, I mentioned these multiple slots. In this product, for example, from Gates Air, this allows you to have a number of options. So you could have 2 ETIs and 2 EDIs, which allows you to mix and match the type of transport stream for streamless switching and automatic failover. They could be all ETIs if that's what you wanted, up to 4 for substantially more path redundancy. Or in the case of RFN, we could come in for gap fillers and transposers. So these same products just have mix and match modules, which allow you to have commonality of spares, which makes it much more flexible. Now, when we look inside the transmitter, you know, probably the first thing you'll notice is a real lack of cables. So while there are a couple that take a sample to the back, they're contained within the RF power module. So the fins you see, the heatsink, that's the RF power amplifier module. It's removable from the back by simply removing a few screws, as is the power supply and the GPS module. All the boards simply plug together and make it for very easy field replacement, very rapid repair. And so that's something that's important to look at in transmitters of contemporary design. Now, as we start to go up in power level, what we're going to see is the same architecture simply scales up. So we use the same low power units as drivers. They drive larger amplifiers, which could give you up to 1.2 kilowatts in about 4 rack units, or nearly 2 kilowatts in about 4.5. Now, these amplifier chassis can be put in a rack together, and we can reach up to 13 kilowatts. So You know, in some parts of the world, DAB runs fewer but very high power sites. This is common, for example, in Australia. And so this is a product platform that works very well in that architecture. Now here's a block diagram of this network topology. So if we look, the red lines represent transport stream. So that's the ETI or EDI coming into the exciters. The green represents control, and then the blue is RF. So these are passively combined multiple amplifiers out to a common antenna. Real-time adaptive correction sample ports, both pre and post filter, and then a fully modular architecture. So not only can the modules be swapped out while they're hot, the power supplies can also be swapped out. Now, when we talk about liquid cooling, similar architecture, high efficiency. So all of these use Doherty amplification from the very low power, which is unique to the products that we're showing you today, through higher power, and that it's broadband, meaning there are no jumpers or tuning to do to go from, say, channel 9A to moving to 12B. It's all the same palette. Now, you know, key characteristics in liquid cooling is making sure that not only do we have high efficiency amplifiers, we need high efficiency power supplies, low power consumption pumps and heat exchangers, and a significant amount of redundancy throughout the system. And we'll take a look at what that architecture looks like a bit. So in these cases, in contemporary designs, full cabinet can be very power dense. Nearly 15.5 kilowatts is the power level available in one rack, downwards, you know, to a couple kilowatts. And so the modules are all hot pluggable and removable. They go to a common heat exchanger and pumps. Now it's also important to note, and this is the case in both the air-cooled and liquid-cooled. To the right, you see kind of this chart with PS1, PS2, and PS3. In this architecture and in contemporary designs, you'll have multiple power supplies. Somewhat unique to the ones we're showing you, we have N+1 power supply redundancy. So if you lose a supply, you're still at 100%, or if you lose two supplies, you're at 50% power. And those power supplies are hot pluggable and removable, which is something to really understand. Some places you have to send it back to the factory for repair. Now the pumps, you know, in contemporary design, they can be located in the transmitter cabinet. They're very compact and low energy consumption. We'd see these are connected using stainless piping and brackets, appropriate shutoff valves and gauges and so forth. That we would see that has dual redundant pumps so that either pump could carry the load. We also have a reservoir, a refilling system. So as you know, in some cases you've got little bits of coolant that evaporate out of the system. In a contemporary design, specifically the ones we're showing you, having a reservoir allows you to have some, even though it's a closed loop system, so it's not just like a big container that fluid is in, it's actually pressurized and closed, but having a reservoir system allows it to refill that so that you reduce your maintenance. Now heat exchangers, you know, some for some products can be very large, but you know, as I mentioned, space is a premium in a transmitter site, so reducing the footprint's a good way to save on your operational costs. Now, in this case, we see a couple different versions dependent upon how much power you're running, both with redundant fans. So the smaller one's about 60 by 80 centimeters, the larger one's about 70 by 96. So as you can see, very, very compact. They can be mounted vertically or horizontally. Now, one thing that's quite unique in the system we offer is there's a programmable auto reversing that periodically will change the airflow to dislodge any debris that might get pulled in. So if you think of pollen and weeds and leaves and things like that, which, you know, normally you'd have to go to your transmitter site to make sure the heat exchanger is clean. This auto reversing allows them to be dislodged early once an hour, a couple times a day, by reversing the airflow, it will clear that and help keep your system clean and operating very efficiently. Now, when we talk about efficiency, just as a refresher, we usually think of power efficiency. So the amount of energy I consume into the transmitter, RF out, and then the rest goes to waste heat. So, if it was 100% efficient, if I put 1 kilowatt in, I'd get 1 kilowatt out. Most transmitters are nowhere near that efficient. And so that's why the reduction of waste energy is important. Not only just because it's we all want to be efficient, use resources wisely, but energy costs are not inexpensive. So, if we look across Europe and the United States, average energy cost is nearly 10 cents a kilowatt hour. And, when we have hundreds of transmitters across a network running 24/7, that all adds up. Now, if I think a little bit about transmitter efficiency, there are some major drivers, but we need to think first, there are some things that we think of as fixed loss. The control system, whether you're controlling a very high power transmitter or a low power transmitter, consumes about the same amount of energy. Similar, the exciter or modulator consumes about the same amount of energy. So in a very large transmitter, it's a very small contributor. In a small transmitter, the control system and exciter is a much bigger piece of it. But that being said, the biggest drivers for energy consumption are the PA modules, the amplifiers. What efficiency level do they run at? Any drivers that might be used, or IPAs in some cases that are referred to. The cooling system, what type of fans and pumps are used? Are they speed controls? And then power supplies, and that can make a big difference. We'll talk a little bit about that. And as I kind of alluded to before, generally low power transmitters as a percentage of efficiency are much lower efficiency or somewhat lower than high power because these fixed losses, such as the control system, the exciter, and so forth, are a much larger portion. So as you might imagine, for a 10-watt transmitter, the energy consumption is dominated by the exciter. For a 10 kilowatt transmitter, it's a very small portion. Now, I mentioned efficiency drivers, power amplifiers. To give you some idea, designs that were new 5 or 6 years ago could give you a PA efficiency between 23 to 33%, which equated in an overall transmitter efficiency of less than 27%, as low as 16. Now, today's designs, it's not uncommon to have Doherty amplification with PA efficiency in excess of 50%. And the overall transmitter efficiency is greater than 40 or 45%. So power amplifiers, probably the #1 contributor. Number 2 is power supplies. So not that long ago, 86% was state-of-the-art efficiency. Today, over the past several years, using some power supplies that we pioneered into the broadcast space, we can achieve 96% AC to DC efficiency. And in a minute, I'll give you an example of how that can make a pretty big impact in the transmitter. And then cooling systems, having the right size pumps and blowers with the heat exchangers really allow you to have the best energy efficiency solution. So I think about power supply efficiency. If we look at the first yellow line, that's indicating the different efficiency of power supplies. So each of these columns talks about an overall transmitter's efficiency. And the bottom yellow line looks at the overall transmitter efficiency. So all the other values remain equal, the same performance of the RF amplifiers and control system. Simply going from 86% to 96% on the power supplies take us from a 34% overall efficiency to 41%. So this is really important to evaluate when you're looking at transmitters. Now, sometimes it's hard to get independent data on that. Some suppliers build their own bespoke power supplies, and it's hard to get separate data. But when you work with your suppliers and ask those questions, it's a good place to start. In these cases, they're hot pluggable, easily removable supplies. These are made by GE. They're available off the shelf, and they're available in virtually every country around the world. Very, very efficient. Now, all this drives what we call total cost of ownership, TCO, and that's kind of how you make a lot of your decisions about what size transmitter and your transmitter investments. So when we think about that, these energy costs all drive into the cost of not only the different parts of the system that convert energy into heat, but then when we think about all the different things that drive into the total cost of ownership, sometimes it's easy to get focused on purchase price, but the cost of delivery, how easy it is to install and commission, training, these energy costs we discussed, repairs, upgrade, disposal costs, all of those goes into, you know, how you decide what makes the most sense for you over the lifetime. Now, when we think about using a total cost of ownership, and before I mentioned liquid versus air cooling, using a TCO or total cost of ownership calculator, we're able to compare a break-even analysis, if you will, of say an air-cooled versus liquid-cooled transmitter. In this case, we take into account you know, all the different costs associated with it, the energy efficiency, and then also the amount of energy you consume to evacuate the heat. So if you were looking at transmitters in lower power levels, typically below 1 kilowatt, air-cooled is the dominant method because the complexity of liquid cooling, there's really not that much heat for it to extract out of the building, and it's hard to get the payoff. For higher power levels, liquid cooling works quite well. Redundancy options, so 1+1 redundancy means main alternate transmitters. I have an exact duplicate. N+1 redundancy is shown in this drawing, says maybe I have 3 multiplexes with transmitters A, B, and C, and I have a shared transmitter that could be switched to any one of these A, B, or C multiplexes. The frequency changed, the program input would be changed, and that way I'm able to share my redundancy costs across a whole group of multiplexes versus having to have a 100% redundancy solution. Now, I may also have dual exciters or dual drivers in a single transmitter, as the exciter sometimes is the single point of failure and the most complex. But really, when we look at redundancy, it's important to evaluate the cost for these redundancies and your tolerance for risk, because it's all in essence insurance. So when we think of N+1, a typical controller like this one that we have, we'll have some sort of front panel indicator, which gives you a simple signal flow of which transmitters are on the air as the standby unit, for example, into a dummy load. That might be manual and auto switches. And then all of these are, you know, on the front panel, all of that's typically shown up on a web GUI for remote operation. And if we think about how these might be connected from a redundancy standpoint, there's this third or overarching controller. So there's each individual transmitter. In this case shows 4, a +1 transmitter, which is the backup, and then a system controller. So it has RF, program, transport stream, and control logic between each of them to automatically monitor if there's a failure, to automatically reconfigure the RF switches, and to put the backup transmitter on the air, and then provide you with some alarms. Now, the other thing I did want to mention, we talked about redundancy, was the link redundancy. So in this case, studio to transmitter links. So if we're using EDI, one way to have redundancy is a technology we use in our Interplex family called dynamic stream splicing. And this allows you to use multiple commodity IP links to use not only additional forward error correction, but to be able to splice bits between multiple streams so that if you have interruption or packet loss on one stream, you can rebuild it with complementary links on the other. So this hitless protection is quite powerful. I was mentioning the ability to have multiple transmitters in a single, or multiple ensembles in a single transmitter. So this is a unique product that Gates Air has. We can do up to 3 DAB ensembles in the same transmitter. So for example, this has 3 adjacent ones we can see in the RF drawing here, or capture of a monitor. Advanced pre-correction allows us to do linear and nonlinear correction and use common amplifiers. So this is ideal if you have say 3 multiplexes, you want to put up a fill-in transmitter in a small area. Instead of having to put 3 transmitters in with RF combining with 3 sets of filters, you can simply have one single transmitter, take 3 ETI or EDI streams in, and transmit the power out. So in this case, it can be as compact as 1 RU, or we can do up to a kilowatt or slightly higher in several RU. It will work in DAB and a or TDMB, basically the same modulation. Again, wideband Doherty amplifier, so very efficient. A GLONASS and GPS built in. So this is a unique way to cost effectively add multiple fill-in transmitters using only one transmitter. Now, the other approach of redundancy, which is a little unique, is this idea of having a one rack chassis with cards in it, using a 7+1 or 6+2. So basically 8 individual transmitters. And in this 4RU chassis, we have all the N+1 switching, shared satellite receivers, shared GPS receivers, which are redundant, by the way, multiple power supplies, and the logic to do the switching. So, again, if you had an area where you needed some low power fill-in, 15 watts or so, but you had several ensembles, very cost-effective way is to use a shared transmitter like this multi-channel transmitter, which significantly reduces your cost to deploy. So some real advancements over where we were just a few years ago. So in summary, there's a lot of options for DAB transmission networks that weren't available not so long ago. Significant advancements in energy efficiency will help you drive down your long-term operating costs. Energy consumption really can be impacted using liquid or air-cooled transmitters. Again, generally, if I have higher power transmitters, those are ideal for liquid cooling. It helps me evacuate the heat outside and saves a lot on building cooling costs. If I have low power transmitters, savings not so great for liquid cooling, and the amount of heat put off is very low. So the simplicity of air cooling generally wins out. There's a number of options for cost-effective redundancy, starting with redundancy in the transmitter itself with multiple power supplies, multiple PAs, dual drive exciters, and then things like N+1 and 1+1 switching. And then there have been some advancements in unique configurations, including multi-carriers on a single transmitter, as well as kind of a multi-transmitter chassis system. All of these really designed to give you flexibility to cost effectively deploy your network. So thank you so much for your time, and I think you'll find that as you evaluate transmitters moving forward, these advancements make it even easier to cost effectively deploy DAB. Thank you very much.
That was Rich Redmond from Gates Air. We've now reached the end of our time. We're a little bit over time, but I'd just like to address a couple of Q&A questions. The first one is from Sanad Solingaram, and he's asking about DAB recordings from Arab States areas, and particularly for extended service labels and DLS. I don't know the answer to that, but I will get the answer, just like the answers to a lot of the other questions that have been raised today. They will be answered and published. I do, however, know that the ETI task force in the technical committee has received some recent ETI streams. So there could be something there that could be of use. So watch this space, please, Sanad. Next one, Paul Boguer, is for Herman. And he asks, looking at cost, which architecture would you recommend for a developing country?
Yes,
Herman?
yes, I'm here. Well, I would recommend a centralized system. It depends on the number of multiplexers, but in general, in a developing country, you start with a few number of multiplexers. And for this, I think the best architecture is to have an architecture with integrated encoders, as presented in you take several minimal systems, as it presented in my presentation. That would be the easiest setup and also the most cost-efficient one.
Okay. Look, I think I'd throw that question also to Arnie, if you'd like to say anything on that space as well.
Yeah, so I agree with Herman. A centralized architecture would be a good approach. So we would basically provide a single server system, off-the-shelf turnkey solution with integrated audio DAB plus encoders, and maybe at the first point only a single system with spare hardware available in case of hardware failure, and later if that DAB transmission is successful, this can be extended by 1+1 redundancy. But I would start off with a turnkey solution, and which can then easily be extended, also functionality-wise.
Yeah. Okay. So yeah, similar answers there. That's pretty a reasonable statements there. I just do one more question, which is to me, and it's about the coding channel rate coding 3A, and the question is Yusuf Al Suleimani about 3A coding compared with other codings. The power level needed is related to what coverage? Well, the answer is quite simple. It's all relative. So if you've got, for example, a 10 kilowatt ERP at 3A to cover a particular area, and you move to more stronger coding at 1A, to get the same coverage area, you use less power, at least a half the power. Now, if you do that for a 1 kilowatt ERP, it's the same answer. It's half the power, or maybe a little bit less. So hopefully that's helped everybody with those answers to those questions. We've several other questions, but we're absolutely out of time. So these questions will be answered, and we'll be posting them after the series is finished. We may be lucky enough to answer some tomorrow if we have some time, because we have extra time tomorrow. So with that, I think I will close the webinar today.
Dr. Les?
And we just got a final comment from Dr. Adnan from the ASBU.
Excuse me, exceptionally, I asked you to give to Dr. Riyad Najm. I saw that he raised the hand. He is a chairman of consultative committee in ASBU, if it is possible. I think he had something to add.
Right. That's a new one. We're working out how to do that.
Dr. Riyad Najm, but I see now he lower his hand. I don't know if he is still. Yeah. He's raising hand.
That's who's it? Dr. Ali
Riyad
Rami?
Yeah, you see blue hand raised beside.
Oh yeah. Just got to find it.
Check the participants list and you see the first name beside his name, blue raised hand.
I'm looking for, oh yeah, I've read name. Okay, yes. Allowed to talk?
Yeah.
Okay, here we go.
But please open his mic.
Ask to unmute. You need to do that. I've asked him to unmute. Dr. Riyad, can you unmute your microphone, please?
I did my unmute. Can you hear me now?
Yes.
Yes.
Can you hear me now?
Yes, Dr. Rida.
Yeah. Okay. Well, thank you very much, and thanks for all the participants for this interesting webinar. My question was, I actually posted it on the Q&A, but I don't know if you have received it or not, but I did post my question. And it has to do with whether, which is better and more cost effective, to have the network designed by one entity and then implemented by another provider, or it is more effective to do both together in order maybe to save time and cost. Which of the two scenarios are more useful and effective? Thank you.
Would like that question? I'll tell you what, I'll give a quick answer, and then if Herman or Arnie would like to add, I'll throw it to them. So I would say it's very dependent on the situation. Some countries prefer to have a single network provider, and they'll have a tender process to establish who that is, and there will be a costing process for that. So it's a competitive bid, and I think that's the important thing, to get the best bang for buck, the most cost-effective solution. You really do need to have a competitive bidding situation, whether ultimately you have a single network provider, as is in many countries, such as Norway, for example, whereas in other countries you'll have multiple elements. In Australia, we're looking now at combining multiplexing and transmission services into one single entity to be more cost effective and well, cost less money. So maybe Herman or Arnie, you'd like to add to that?
Yes, so I can maybe add something on the technical side, but so mainly it really depends, as Les said, on the situation. So even in Germany, we have different scenarios. In some of the multiplexes we have, there are a number of commercial radio stations, and there is a separate network operator. So it's a contractual thing often, and it's also a matter of who is responsible contractually for what part of the transmission chain. And at the other side, sometimes there are also DAB platforms which are completely operated by a single broadcast institution. So it really depends on legislation, on rather than on technical aspects.
Herman, would you like to add to that?
Yes, sorry. Yes, yeah, I can tell how it's in France. It's because in France, yes, you know, we have the major player in France is TDF. I know, for example, in a country like Algeria, you have a TDA, which is very similar. And it depends a little bit. So they have 80% of the market for the transmission. So it depends. If you have a big rollout in the beginning, then probably you need to have a big player that can you know, build up the complete transmitter infrastructure. But if it's, for example, for smaller multiplexes that we have in France, each multiplex is, as you said before, less in an open tender. And this gives also room for smaller players on smaller, but in this case, system integrators, to build up a complete system with 1 or 2 transmitters, which is, yeah. So it makes the situation here in France quite competitive, and it enables DAB to you know, France we do DAB, but it's I think it's not very expensive for the radio stations here.
That's good.
This helps.
I'll add one more point to that. Now with extensive digital connectivity, IP connectivity, the location of multiplexing systems is changing. And I've seen the use of data centers and virtualization now come into play quite strongly in some countries, including Australia, where rather than having that equipment housed in a centralized system, for example, at a high power transmission site, it's actually cheaper to actually relocate all that functionality of the multiplexing and encoding, control and monitoring to a data center and a virtualized system, and then just connect the EDI stream to the actual transmission site where the transmitter must be. So it's a changing world, and I think all these things need to be considered in the context of the requirements of the day. If it's a very simple start and all you need is one site with a a few transmission services, maybe 10 or 15 services, it could well be cheaper to just do it at the site. If you've got a complex multi-site network, it could well be the exact opposite of that. And what is actually cheapest is to use a data center centric solution, or even decentralized solution for a case of data disaster recovery. So as we say, every country's different and every budget's different. So it always counts on that as well. So I hope that helps answer your question, Dr. Ria.
Yes, thank you very much. Thank you. We appreciate it.
Okay, thank you. Well, with that, I think, Dr. Adnan, we might close the session today. Thank you to all the participants, all the attendees and the panelists. Thank you for your time. I hope you've got something out of this. You will have seen several email addresses and website addresses, including that of WorldDAB and ASBU. If you have any further questions after this webinar is over, please don't hesitate to send them through, and we'll amalgamate them with the other open questions as well. Remember, we have the final session of this series tomorrow. We will start with network design with Jerome from TDF, and a bit from me on signal frequency network design. And then we'll be talking about receivers, both domestic from Frontier and also automotive from AATT. So, so please join us again tomorrow. And thank you for the time today, and hope to see you then. Thanks a lot. Bye-bye.